Hello, everyone, and welcome to Chapter 5. It's time to talk about mixtures. So until now, we've mostly been focusing on pure phases and pure states. However, it turns out that not all chemistry is just, well, pure. Most of the time, we're dealing with mixtures, and so we have to take a close look to see how a lot of our thermodynamic properties change as soon as I start adding in extra systems. So one of the first things we're going to have to start with is figuring out how to examine a simple system. So the simplest case we can usually end up with is a two-component system. We need to know exactly how many variables I need in order to perfectly define the system. So I knew if I had, say, a simple ideal gas, I could define the system by two variables if I don't include the amount or moles of the system, as demonstrated with our uh, good old phase rule, where if I have a single component in a single phase, this gives me a variance of 2. And this is traditionally treated as I measure the temperature and the pressure of the system, perfectly defining the molar volume. However, things get a little bit messier once when I add in an extra component. Because when I add in an extra component, this gives me an extra degree of freedom. So if I say look at my simple gas mixture of O2 and N2, so the simplest approximation I can have for an effective atmosphere, this gives me essentially 3 degrees of freedom. And we often define this mixture in terms of pressure and temperature, um, just like I did for the single component. But this gives me a third state variable. So in order to perfectly define my system, I need a third state variable that defines the mixture. So we need a good way to describe the components of these mixtures. Now, one of the big things we're going to want to do is we want a size-intensive property. Because a lot of the times when I'm dealing with a mixture, like say an atmospheric mixture, if I have a size extensive property, that only works if I know the size of my sample. So we're going to much prefer to have something more size intensive. So this immediately takes away options like moles or mass of material. However, in addition, we want it to be able to describe each component separately. Oftentimes, this is because I'm only interested in a single component. So this often is going to give us a unit of concentration. So concentration is often going to be the best way to satisfy these conditions. However, it turns out if you look back through what we've covered so far, we haven't actually demonstrated many units of concentration that are going to adequately satisfy a lot of our thermodynamic properties. Because in truth, there actually isn't many. However, we've already used one type of metric at the end of our conversation on thermodynamics, and that's mole fraction, which again, just as a reminder, is going to be the moles of the component I'm interested in over the total number of moles. And it also is perfectly defined for a two-component system because we have the mole fraction for each component when added up should give us 1. So if I have a two-component system, I only need 1 mole fraction. However, when we have a 3-component system, I'm going to need 2 separate mole fractions to perfectly define the third. And you may notice this actually perfectly matches up with what we just saw previously with our phase rule. So mole fraction is a very good metric for trying to define a mixture of a system. And one of the reasons why is that it's fairly universal and it has a very good grounding in thermodynamics. And you're going to see this as we proceed, that when treating a lot of thermodynamic systems, the function that most naturally pops out is going to be mole fraction. However, it is occasionally tricky to work with on an operational level, as we often have a hard time measuring, say, the total number of moles present in a system. I can do it for gases by making use of partial pressures, as long as they're ideal, but as soon as we get away from that, it gets a little bit more messy. So specifically if I'm handling dilute systems, we often have a good stand-in. Now, when I'm talking about dilute systems, this is going to be systems where there's a clear solute, So there's a clear minority component and a clear majority component. Mol and under these conditions, molality actually turns out to be a good alternative. And this is going to be very important because when I define molality, I'm going to be defining it in terms of a solute and a solvent. So this works great with, say, something like beer, where I have, say, a 6% mixture of ethanol in water. So it's majority water. However, by the time we get to, say, something like vodka, it gets a lot messier because we're now in the realm of 50-50, and it's hard to tell who your solute is and who's your solvent. However, as long as I have a dilute system, so a clear solute, then I can essentially define the system in terms of moles of the solute and mass of the solvent. And one of the reasons why this is a good stand-in for mole fraction is that I can actually end up inserting mole fraction into this expression. For example, the moles of my solute are going to be the same as the mole fraction of the solute times the total number of moles of the system. Well, and for when I'm looking at the mass of the solvent, well, this is going to be the same as the moles of the solvent times the molecular weight. Now, the moles of the solvent can be essentially given as the total number of moles times essentially whatever the mole fraction of my solvent, which is just 1 minus x. Because again, we have this wonderful feature that if it isn't B, it's going to be A. So we can define that with this ratio and then move our way back towards total mass. Now, one of the things you may notice here is that total number of moles appears both on top and on bottom. So they end up canceling out, giving us a more simple expression relating the molality to the mole fraction. But you may notice it's a little bit tricky, as mole fraction shows up both on top and on bottom. However, you can go ahead and rearrange this equation to isolate the mole fraction of the solute in terms of this kind of combined function of the molality of our solute times the molecular weight of our solvent. And this may actually seem like a little bit of an awkward metric, but it turns out that if we actually kind of focus in on this molality of the solute times the molecular weight of the solvent, we can actually get some real insight into both mole fraction and molality and really what they're telling us. So if I look at the units on both of these, when I look at the molality, again, this is moles of B times mass of A in kilograms, whereas the molecular weight provides me the mass of A in grams over the moles of A. Well, you're going to notice that I have mass of A in both the top and the bottom. So as long as I accommodate for essentially some unit conversion of 1 over 1,000, because I have 1 kilogram per 1,000 grams, and we can essentially multiply by 1 kilogram over 1,000 grams to finish out canceling our units. And what this really shows me is that this combined molality of solute times molecular weight of solvent really gives me a ratio of moles of moles of the solute to the moles of the solvent. And that's really what this combined function ends up giving us. And so really when I'm looking at the mole fraction, I'm essentially looking at the ratio of the two species over 1 plus the ratio of the two species, with some funniness going on with the units and some conversion factors that end up canceling out. However, one of the things that's actually kind of cool is that molality is actually going to provide us with very similar information. Molality is going to provide us with very similar information to this combined molality and molecular weight function. The only difference is that it's unit transformed. So really, even though I have mass on in the denominator, I'm really still just looking at moles of solvent, solute to moles of solvent. And this is one of the reasons why molality is actually fairly useful, is it's just going to give us a ratio of moles. So in that case, it's almost as good as mole fraction, but it does require the assumption that we do actually have a solvent. But if you're working under these conditions, it's a fairly useful metric. However, there's also one other form of concentration that's a little bit peculiar to physical chemistry, but will occasionally pop up here and there, and that's partial molar volumes. So the idea of partial molar volumes is what you're looking at is how much the volume of your solution changes as I add one of my components. So as I say, I'm adding species J to a general total solution. As I start adding adding J, I should start to see some increase in the volume of the system. However, sometimes you may end up encountering a odd behavior, which is you add more of J, then it may start causing the volume of the system to contract based on kind of the nature of intermolecular forces. And you'll occasionally see some examples of this, often when working with dilute amounts of salt. However, one of the important parts of this is that it is going to have make several assumptions. One of the major ones is that we're assuming that pressure and temperature stay fixed, because again, we need to have previously fixed two variables. However, there's a very important third variable that also needs to be fixed. This is operating under the assumption that the total number of moles of all other components are being held constant. And as a result, one of the things that this ends up helping tell me is how the volume is going to change with the addition of J. But because all the other moles are, the moles of all the other species are being held constant, really what's happening is I'm adding J is I'm changing the ratio. So a good way to try and think about this is that the partial molar volume is going to show a dependency on pressure, temperature, and the ratio of the species of interest to all the other species present. So again, under a dilute system, this would be the relative ratio of solute to solvent. However, we can actually get a little bit more insight when looking at partial molar volumes by looking specifically at a two-component system. So if I've got a two-component system based on the nature of derivatives, what I can do is define the change in the total volume of the system times the molar volume of A times exactly how much of A I'm adding, plus the molar volume of B times the exact amount of B that I'm adding. Now, what you can do is really get some more insight by integrating the system from essentially 0, where I have no component of either, so 0A and 0B, up to the final system that I actually care about. Now, what actually is very important is that we're making the approximation at this point that our partial molar volumes of A and B won't change. But because we're already making the assumption that A and B are the values of the partial molar volume of each species is going to be dependent on temperature, pressure, and ratio of the component. As long as you have the exact ratio of components present, then then we can essentially treat it as independent of the exact number of moles present. So you can pull that out of the integral. And thus we have a simple integral of 0 to V and 0 to NA. So these three integrals become relatively trivial, giving us a summary equation of the total volume of the system is going to be dependent on the sum of the partial molar volumes of each component times the amount of each component. And really what this ends up telling me is in practice, the partial molar volume is going to be a metric of how much volume 1 mole of, say, the relevant species occupies. So if I say have 1 mole of A and 1 mole of B, then it's simply going to be the addition of the two partial molar volumes. And so we often like thinking about it in such terms, but there is a notable oddity that happens, is that occasionally, especially when dealing with some salts, it's possible to have a negative molar volume. Now, this doesn't mean that, say, species B, or my solute, doesn't occupy any volume or occupies negative volume. Really, what it's telling me is that as opposed to, say, kind of a pure species, it's causing A to essentially have uh, a much lesser volume than you would naturally expect. Though it is worth noting that these cases of a negative partial molar volume is still kind of rare. So let's go ahead and take a look at kind of the significance of partial molar volumes in, say, a real case. So let's go ahead and take a look at a mixture of water and ethanol. So if I have a pure system of ethanol, well, my mole fraction of ethanol is going to be 0. And at this point, water has a partial molar volume of just over 18. It's relative, that's going to be essentially the volume occupied by 1 mole of pure water. However, fun things start happening when you end up adding in a little bit of ethanol. And that's more or less the fact that water is going to start uh, possessing a much greater molar volume than you would naturally expect. And the reason why stems largely from the fact that, well, there's now a whole bunch of nonpolar regions present in the water that are essentially pushing the water out. However, as you essentially start adding in more ethanol, it breaks up the lattice structure of the water, and you start seeing a decreasing partial molar volume, as it's essentially occupying much less volume than you would naturally expect. And you see a very similar trend, except in the reverse direction, when you're looking at the partial molar volume of ethanol, with the notable exception that now the ethanol occupies a much smaller portion of the volume than you would naturally expect if the two ratios were essentially fixed. So again, partial molar volume, it's a little bit of an odd concept, but it's going to be a very useful metric as and way to think about the system, as we're going to try next time applying some very similar concepts to free properties of free energy. Till then, take care.